Hey everyone, and welcome. If you're a programmer, you know that tree algorithms are, well, they're pretty much the foundation for a ton of complex systems. Today, we're going to dive deep into a classic problem, how to find the longest path, or what we call the diameter, of a tree. So let's jump right in.
Think about it for a second. A computer network, your social media feed, even the roads you drive on, they all have this one big question lurking inside them. What's the absolute maximum distance between any 2 points? That's exactly what we're going to answer today, and we'll do it by exploring the really elegant structure of a data tree.
All right, so before we can start running and finding the longest path, we've got to learn to walk. That means we need to be super clear on what a tree actually is in this context. And trust me, getting these fundamentals down cold is absolutely key to solving the harder stuff, especially when you're on the clock in an exam.
Okay, write this one down because for any exam, this definition is non-negotiable. A tree has 3 rules it must follow. First, it's a connected graph, meaning you can get from any node to any other node. Second, it has this very specific ratio, n nodes and exactly n-1 edges. And third, and this is the big one, it's acyclic. No cycles, no loops. You can't start at a node, walk around, and end up back where you started. This structure is what guarantees that there's only one unique path between any 2 nodes.
So a plain old tree is fine, but we can make it way more useful by rooting it. All you do is pick any node you want and call it the root. And just like that, you've created a hierarchy. It's like picking the great-great-grandparent at the top of a family tree. Suddenly, everything flows down from that one single point.
And once you have that root, you get this whole new vocabulary to talk about the tree. The node right above you, that's your parent. The ones below, those are your children. Here's a simple rule. Every single node has exactly one parent, except for the big boss, the root, which of course has none. This is the language we'll use to navigate the tree from now on.
All right, so we've got our definitions down. Now, let's get to the main event. We're here to solve the tree diameter problem. And you're going to see this one everywhere, from classic computer science problems to those tricky technical interviews. It's a big one.
So what exactly is the diameter? It's actually a really simple idea. It's just the longest possible path you can find between any 2 nodes in the tree. Think of it as the ultimate scenic route, the longest walk you can take from one point to another within that network. So let's look at an example. Imagine you start at a node we'll call 6, and you want to get all the way over to node 7. You might have to travel through nodes 2, 1, and 4 to get there. If we count the edges, the number of steps we take, we see that the path has a length of 4. If that's the longest journey possible in the whole tree, then boom, the diameter of that tree is 4.
Okay, that's the what. Now for the how. How do we actually write code to find this diameter? Well, the good news is we've got 2 fantastic, super efficient algorithms in our toolkit. Both are great, and both get the job done.
And what's cool is that they approach the problem from totally different angles. First up, we have dynamic programming. Think of this as the methodical, systematic builder that constructs the answer from the ground up. Then, we have a really slick method that uses 2 passes of a depth-first search, or DFS. This one's more like a clever and elegant shortcut.
So let's walk through the dynamic programming approach. First, you just pick any node, it doesn't matter which one, and call it the root. Then, for every single node X in the tree, you do a little calculation. You find the longest path going down from it. With that info, you can then find the longest path that uses X as its highest point, its peak, by just adding together the 2 longest downward paths from its children. You do this for every node, and the biggest value you find, well, that's your diameter.
Okay, now for algorithm 2. And honestly, this one feels like a magic trick, it's so simple. Step 1, pick any node. Seriously, any node you want. Call it A. Now run a DFS from A to find the node that's the farthest away from it. Let's call that node B. Here comes the magic. Run a second DFS, but this time you start from B. The farthest node you can find from B, we'll call it C, gives you the answer. The path between B and C is a diameter of the tree. That's it. You're done.
I know what you're thinking. That's way too simple. There has to be a catch, right? How can that possibly work every single time? Well, it's not magic. There's a really solid proof behind it, and understanding the why is what separates just knowing an algorithm from truly understanding it.
So here's the secret sauce, the big idea.
It turns out that no matter which random node you start from, the node that's farthest away from it has to be one of the two endpoints of an actual diameter. So that first DFS you do, it's like a homing missile that locks onto one end of the longest path. And once you're there, the second DFS is just a simple walk along that exact path to find the other end. It's beautiful, right? So simple, but so incredibly powerful.
Okay, theory is great, but let's get practical. How do you use this knowledge to ace an exam or nail a technical interview? Because knowing the steps is one thing, but executing them perfectly when the clock is ticking, that is a completely different challenge.
All right, quick-fire review. These are the definitions you absolutely need to have on the tip of your tongue. A tree. It's connected, acyclic with n nodes in n-1 edges. Got it? A rooted tree. Just a tree where one node is the boss, the root. Parent-child. That's the language of the hierarchy. And the diameter, the longest path between any two nodes. Get these locked in.
Now let's talk about the traps, the common mistakes people make. With the 2DFS method, the #1 error is starting the second search from the wrong node. You must start it from the farthest node you found in the first search. No exceptions. Another tricky one is assuming paths only go down from a parent. They don't. A path can go up toward the root and then back down another branch. And finally, under pressure, it's so easy to mix up the logic of the two algorithms. Keep them straight in your head.
So there you have it. You now know how to find the longest path in any tree. But this brings up a much bigger, more interesting question, doesn't it? In a real-world network, is the longest path always the most important one? Or is it maybe the one that's most central, or the one with the most traffic? The diameter is a vital measurement for sure, but it's often just the beginning of understanding the true, complex story that a network has to tell.